Let's do a couple of examples. In the first example here, we are just finding the angular momentum of the bowling ball. So this is just a plug and chug to use that definition. The definition of angular momentum equals I omega. We need to find I and omega. I is equal to the moment of inertia of a solid sphere. We assume it's solid. We ignore the finger holes. That's 2/5 mr squared. So we can plug in what we are given. We have 2/5 times 7 times 0.12, the radius here, 0.12 squared. And that's going to give us 0.04 kilograms times meter squared. And then we need the angular velocity, which is 10 revolutions per second, but we need to convert that to radians per second. So we know that 1 revolution is 2 pi radians. So we multiply 10 by 2 pi, we get approximately 6.28. Don't round the calculator, and then we just multiply the two numbers together, 0.04 times 6.28, and I got 2.53 kilograms meter squared per second. So this was just a plug and chug using the definition. This is the amount of angular momentum that it has. The faster it's rotating, the more angular momentum it would have. Let's do one last example using conservation of energy. So this is a fun one that I actually do this as a demonstration in class, where I have a rotating stool and I ask a volunteer to come up and hold some weights, and then I spin the volunteer and I tell him or her to bring their arms in, and then the person spins faster. It's kind of fun because sometimes they lose their balance a little bit, but they end up spinning very quickly sometimes, so it's pretty impressive. Let's take a look. A student in Dr. Walker's physics class spins on a rotating stool while holding a 5 kilogram weight in each hand. He begins with his arms straight out from his body and his hands 140 centimeters apart. While spinning at 2 revolutions per second, he pulls the weights in and holds them 50 centimeters apart against his shoulders. If we neglect the mass of the student, how fast is he spinning after pulling the weights in? So whenever you visualize something that's spinning and then the moment of inertia is changing, then you want to think of conservation of angular momentum. Let's go ahead and write down our givens here. It says to ignore the mass of the student, so we're just going to consider the weights. We're going to treat them as particles, and because we're not given any information about their size or shape, so we have to treat them as particles, and those are the two objects that are moving inward, changing the moment of inertia of the whole thing. So the mass of each one, I'll use a little m for particle, is 5 kilograms. And initially, how far are they from the axis? The axis is here. It says the hands are 140 centimeters apart. That means that they're each 70 centimeters away from the axis, halfway. So the initial r is 0.7 meters. And then when he brings his arms in, it says that now the hands are 50 centimeters apart. Now this picture, doesn't show them on the shoulders. This was the best picture that I could find. But we're just assuming, based on the picture here, that they're 50 centimeters apart. That means that the halfway is 25 centimeters, or 0.25 meters, is the distance of each one. If they were at the shoulder here, that's the distance right here, RF, from the axis to that weight, which is at the shoulders. And we are also given the initial, omega initial, is 2 revolutions per second. And we're trying to find omega final. So usually we have to convert that angular speed to radians per second. But in this case, because it asks for the final angular speed also in revolutions per second, we see that in our equation for conservation of angular momentum, I initial omega initial equals I final omega final, that nothing is squared or anything. So if you leave the omega initial in revolutions per second, it just means that the omega final will be in revolutions per second. And we're just going to make sure we're in standard units for the moments of inertia, which we are because we have kilograms and meters. So for particles, the moment of inertia is the sum of mr squared, if you remember our definition for particles. So there are two weights on, right, there's a weight on either side. So the total moment of inertia at the beginning is mr initial squared plus mr initial squared, because there are two masses and they both have the same mass of 5 kilograms. And then we have omega initial, then we have the same thing for the final, and I'll just write it the same way, mrf squared plus mrf squared. I don't have to write 1 and 2 because they're the same. That's going to be multiplied by omega final. So the initial moment of inertia, you're going to plug in the 5 times the 0.7 squared, and then you're going to do that again, so multiply that by 2 or just add it together. And just since I got numbers, I'll go ahead and write them. I got 4.9 for the initial moment of inertia, and that's going to be multiplied by omega initial. And then the final moment of inertia, when I plugged in the 5 times the 0.25 squared plus 5 times the 0.25 squared, I got 0.625, which makes sense. The moment of inertia got smaller because the weights got closer to the axis of rotation. And now we can solve for the final omega. So we're going to go ahead and do 4.9 multiplied by 2 revolutions per second. I just wanted to show you how the units work out here. Divided by 0.625. The units for the two moments of inertia cancel out, and you can see we're left with revolutions per second. So we did not need to convert in this case, and I got 15.7 revolutions per second. So close to 16 revolutions per second, when initially he was only rotating at 2 revolutions per second. So it is an impressive demonstration. That's the end of this video. So just to recap, if you have an object that's rotating and its moment of inertia is changing because the mass is moving around, then use conservation of angular momentum and you can figure out how the angular speed changes based on how the distribution of the mass changes.